In this lecture, I am going to explain you different types of solids. As you are aware that there are two different types of solids, crystalline solid and amorphous solids. Let's see what is called crystalline solid first. This crystalline solid has definite orderly array of atoms, ions or molecules in the three dimension. It has definite orderly array of atoms or ions or molecules in three dimension. Let me draw the diagram for crystalline solid. This circle which I am drawing is representing either atom or it can be ion or it can be molecule. So this is the array of atoms, ions or molecules. And as you can see in this case, they are repeated at regular interval in the two dimension in this case. Actually in the crystal it is three dimension. Let me show the bonding to them. So this is two-dimensional crystal diagram of the solid, crystalline solid. As you can see that there is an orderly arrangement of either atoms or ions or molecules, which is called the crystal lattice. What I have drawn is called crystal lattice. So crystal lattice is nothing but orderly arrangement of atoms. Or ions or molecules in three dimension. That is called the crystal lattice. For the crystalline solid, periodicity is essential feature. As you can see, these atoms, or you can say any unit, repeated at regular interval. As you can see here in this diagram, it's a position of atom, or in that matter any unit. That unit is the circle which I have drawn here. That circle represents either atom, ions or molecules. So position of atom or any unit repeated in space at regular interval. It means which is called translational periodicity. This is called translational periodicity. Translational periodicity is any atom or a group of atoms are repeated in space at regular interval. So this periodicity is essential feature of crystalline solid. Periodicity is essential feature of this crystalline solid, and this periodicity can extend to many atomic distance. In case of crystalline solid, the periodicity extends to many atomic distance. And so we say that crystalline solid has long range order. So we can say that crystalline solid has long range order. What is this periodicity which extends to many atomic distance means? Suppose these are the atoms which I am drawing here. They are extending. This periodicity of which is extending to many atomic distance. This is many atomic distance. So while these crystalline solids are formed due to sudden change in the surrounding of that, there may be some defects occur in the crystalline solids. So in this case, this periodicity is slightly disrupted and its position changes. And again, it extends to many atomic distance. So initially, these atoms were repeated, or you can say this periodicity extended to this many atomic distance. Later, it changes slightly and again extends to many atomic distance. And so this is called long range order. So all the crystalline solids have long range order. Another important property of this crystalline solid is it has definite melting point. That means that it sharply changes from solid to liquid at particular temperature, which is the melting point of that solid. Also, the crystalline solids have typically flat surfaces with unique angle between them. There is a unique angle between the faces, and they have flat surfaces, and because of that, these crystalline solids have unique three-dimensional shape. I will give you some examples of crystalline solids. Minerals are crystalline solids. Sand, sugar, clay, limestone, metals, and carbon in diamond and graphite form. So these are some examples of crystalline solids. Then there are two different types of crystalline solids. Crystalline solids, there are two different types. The first type is polycrystalline. Polycrystalline solid, and the second is single crystal, or we can call it monocrystalline. So there are two types of crystalline solids. Let me draw first diagram for the polycrystalline solids. What I am showing here is the boundary between the different crystals, and I am going to show you the orientation of atoms or ions in the crystals. So these circles can be ion, atom, or a group of atoms. Let's say they are atoms. Then you can see the orientation of these crystalline solids. So this is the orientation in this direction, in this part of the polycrystalline material. Then in another part, let's say they are oriented in this fashion. So in this second part, as you can see, they oriented in this direction. And in the third part, let's say they are oriented in this direction. Atoms are oriented in this direction. So in this diagram, I have shown you the three different type of orientation. Each block which has a same orientation is called the crystallites. So these are called crystallites, or they are also called grains. And in this diagram, I have shown three crystallites. And these three crystallites are separated by well-defined boundaries called the grain boundaries. So this is the boundary between the crystals, and that is called grain boundary. So let me draw the diagram for single crystal. As the name implies, in certain part of the material, there is only one type of orientation of atoms. There is only one type of orientation of atoms throughout the material. Only single type of orientation is there. Then that is called monocrystalline or single crystal. Let us see the difference between these two. As you can see here, in case of the polycrystalline material, I have shown only the three crystallites, but in the material there are tens of millions of crystallites present. So you can say that in polycrystalline material is nothing but it is the aggregate of number of small crystallites. Aggregate of number of small crystallites, and we can see there that they have different orientation. So all these crystallites are completely random orientation. Also, they are separated by well-defined boundaries. I can say that grains or crystallites separated by well-defined boundaries called grain boundaries. But in case of single crystal, as you can see clearly that in the single crystal, the sphericity extends to extends throughout the material. There is the same orientation throughout the material. Only one type of orientation present. So you can say the whole solid is one crystal. There is no internal boundary. As you can see, there is no internal boundary. Only boundary is external surface. Surface is also a kind of boundary. So that is the difference between polycrystalline and monocrystalline solids. One more difference is, these polycrystalline materials are more stable compared to single crystal, and single crystals are less stable compared to polycrystalline materials. Polycrystalline materials are having isotropic properties. So they are isotropic materials. See, in this case, a single crystal, if you select only one crystal or one grain, then that grain, that crystal, will have a different properties in different direction. Properties like mechanical properties, optical properties, and electrical properties would be different in different direction for single crystal. But as in polycrystalline materials, there are tens of millions of tiny crystals present with completely random orientation, and so properties are averaged out, and so polycrystalline materials are isotropic, but single crystals are anisotropic, means they will have different properties in different directions because concentration of atoms is different in different directions, so they have different optical, mechanical, or electrical properties. I will give here some examples for polycrystalline materials. All metals, all common metals. Many ceramics, rocks, ice, etc. These are some examples of polycrystalline materials. Then for single crystal, I am giving the example for naturally occurring single crystals. We can grow single crystal in the research lab also, but I am giving here the example of naturally occurring single crystals. For example, quartz is single crystal, then topaz is monocrystalline, salt, diamond, and Iceland spar. These are some examples of single crystals. So as we studied, the crystalline, what is a crystalline solid and what are the different types of crystalline solids. Then I will explain now amorphous solids. Second type of solid is amorphous solids. In amorphous solids, let me show the diagram. There is a complete random arrangement of atoms or molecules of ions like this. Okay, there is completely random arrangement of atoms, ions, or molecules. Atoms, ions, or molecules. And as shown in the diagram, it is randomly arranged. Atoms or whatever are there, like ions or group of ions or atoms, they are randomly arranged in amorphous solid. And as you can see in the diagram, there is no symmetry, there is no periodicity. So translational periodicity is absent there. No translational periodicity is there. But if this translational periodicity is present, if translational periodicity is present, then it extends to few atomic distance. Which is called short range order. So amorphous solids have short range order. In this case, let's say that in this direction there is some periodicity or some here is there. So some periodicity is present. If at all it is present, generally it is absent. But if at all present, it extends to very few atomic distance. And so we say that amorphous solids have short range order. There is no definite melting point. That is, some parts melt earlier compared to the others. So it takes some range of the temperature to melt down the amorphous solids completely. And of course, they are isotropic. They are isotropic because properties are averaged out. There is a completely random arrangement of atoms in this amorphous solids, and so the properties are averaged out. And so we can say that they are they have isotropic properties. Some examples of amorphous solids: glass, then resins, both natural and synthetic, then sulfur in powder form, there is amorphous carbon, there is amorphous silicon also, and most of the plastics. Most of the plastics are amorphous. So these are examples of amorphous solids. So in this lecture, we have studied different types of solids: amorphous solids and crystalline solids. In crystalline solids, there are two types: polycrystalline and single crystal.